The allure of faster-than-light travel has always captivated the human imagination. Tales of zipping through the cosmos at unimaginable speeds fill our science fiction literature and cinema. Yet, according to conventional physics, the speed of light remains the ultimate speed limit. This constraint, firmly established by Einstein's special theory of relativity, poses a significant hurdle for interstellar travel. In the realm of conventional physics, nothing can surpass the speed of light. Any object with mass would require infinite energy to reach this speed, effectively making faster-than-light travel impossible. This barrier has not deterred scientists and dreamers from hypothesizing about ways to circumvent it. One such hypothesis involves bending the very fabric of spacetime itself. The concept of using spacetime distortions to achieve faster-than-light travel brings us to the idea of a spacetime bubble. Could this theoretical construct provide a workaround to the speed of light limit? As we delve into the intricacies of spacetime bubbles, we uncover both the promise and challenges of this fascinating concept. It is a journey that straddles the line between current scientific understanding and the speculative frontiers of theoretical physics. The notion of a spacetime bubble has roots in the quest to bypass the speed of light barrier. At its core, this concept involves a region of spacetime that can move faster than light relative to the external universe. Essentially, it is a bubble that carries its contents through space at superluminal speeds. Imagine a spacecraft enclosed within this bubble. The spacecraft itself does not exceed the speed of light. Instead, the bubble of spacetime it resides in moves, theoretically allowing for faster-than-light travel without violating Einstein's speed limit. This idea hinges on manipulating spacetime itself. By contracting space ahead of the bubble and expanding it behind, the bubble moves forward, dragging the spacecraft along with it. This approach could potentially allow for faster-than-light travel without the spacecraft itself accelerating to those immense speeds. Yet, the concept is fraught with challenges and remains firmly in the theoretical domain. The physics underlying space-time bubbles are complex and require significant advancements in our understanding and technology to become feasible. Understanding how a space-time bubble could be created and controlled is a critical area of research. The Alcubierre Drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical model for a space-time bubble that allows a spacecraft to travel faster than light. It contracts space in front and expands it behind, moving the bubble itself. The spacecraft remains stationary within the bubble. The bubble moves, carried by the manipulated fabric of spacetime. The drive relies on a solution to the equations of general relativity. It imagines a wave carrying the bubble forward. It requires exotic matter or negative energy density. Despite speculative concepts, it offers a glimpse into faster-than-light travel. The theoretical basis for the Alcubierre Drive is deeply rooted in Einstein's general theory of relativity. General relativity describes how mass and energy warp the fabric of spacetime, creating the gravitational fields we observe. This warping of spacetime is what the Alcubierre Drive aims to exploit for faster-than-light travel. The drive's concept of contracting and expanding spacetime aligns with the principles outlined by general relativity. According to Einstein, massive objects cause spacetime to curve, and this curvature affects the motion of objects within that space. By extending this principle, the Alcubierre Drive proposes that spacetime itself can be manipulated on a smaller, more controlled scale. In the context of the Alcubierre Drive, the spacecraft does not move through space in the traditional sense. Instead, space itself moves, carrying the spacecraft along with it. This motion is achieved by creating a warp bubble that distorts spacetime around the spacecraft. This approach leverages the flexibility of spacetime as described by general relativity. The mathematics involved are complex, but they show that under specific conditions, such distortions are theoretically possible. By connecting the Alcubierre Drive to the well-established framework of general relativity, physicists can explore the potential and limitations of faster-than-light travel within the bounds of known physics. This connection also highlights the immense energy and exotic material requirements for such a drive to function. Section 5. Spacetime and the light speed loophole. Spacetime manipulation offers a fascinating loophole regarding the speed of light. Conventional physics states nothing can travel faster than light. However, spacetime itself isn't bound by this limit. The Alcubierre Drive's warp bubble exploits this loophole. The bubble can move at superluminal speeds while the spacecraft inside does not. This is because the fabric of space-time is moving, not the spacecraft. This loophole suggests a pathway to faster-than-light travel. Section 6. Energy requirements and exotic matter. A significant challenge for the feasibility of the Alcubierre Drive and space-time bubbles is the immense energy required to create and sustain them. According to theoretical calculations, the energy needed to warp space-time in the manner proposed by the Alcubierre Drive is astronomical. It far exceeds the energy output of any current or foreseeable technology. The drive's reliance on exotic matter or negative energy further complicates the picture. Negative energy, a concept predicted by quantum field theory, has yet to be observed in practical applications. Exotic matter, with properties that differ significantly from ordinary matter, remains a purely theoretical construct. These exotic forms of matter are essential for creating the negative energy density required to generate the warp bubble. Without them, the drive cannot function. The search for and potential creation of exotic matter is a significant area of ongoing research in theoretical physics. Furthermore, even if exotic matter or negative energy could be harnessed, the quantities needed are staggering. The energy to sustain a warp bubble capable of carrying a spacecraft would require resources on a scale currently unimaginable. Thus, while the theoretical framework for the Alcubierre Drive is intriguing, the practical challenges are immense. The energy requirements and the need for exotic matter remain significant obstacles that must be overcome for faster-than-light travel to become a reality. Section 7. Future prospects and theoretical breakthroughs. Despite the formidable challenges, the future prospects for space-time bubbles and faster-than-light travel continue to inspire researchers. Advances in our understanding of quantum mechanics, general relativity, and high-energy physics may provide the breakthroughs needed to overcome current limitations. One potential avenue of research involves the study of quantum field effects and their implications for negative energy. Discovering or creating negative energy in a controlled manner could pave the way for the practical application of the Alcubierre Drive concept. Another promising area is the ongoing search for new forms of matter. Exotic matter, if discovered, could provide the necessary conditions for faster-than-light travel. Research into high-energy particle collisions, dark matter, and other frontier areas of physics may yield the insights needed to create or harness exotic matter. Moreover, advancements in energy generation and storage technologies could help address the immense power requirements for creating and sustaining a warp bubble. Breakthroughs in fusion energy, antimatter propulsion, or other novel energy sources could provide the necessary power. While these prospects are speculative, they highlight the potential for future breakthroughs that could transform faster-than-light travel from theory to reality. The quest for faster-than-light travel continues to push the boundaries of our scientific knowledge and technological capabilities. Section 8. Implications for interstellar travel and human exploration. The realization of faster-than-light travel through space-time bubbles would have profound implications for interstellar travel and human exploration. It would open up the cosmos in ways previously thought impossible, allowing humanity to reach distant stars and potentially colonize other planets. A functioning Alcubierre Drive could reduce travel times to neighboring star systems from tens of thousands of years to a matter of months or even weeks. This would make interstellar exploration and the search for extraterrestrial life feasible within a human lifetime. The ability to travel faster than light would revolutionize our understanding of the universe. It would enable the direct observation and study of distant celestial phenomena, providing new insights into the nature of space, time, and the cosmos. Furthermore, faster-than-light travel could have significant implications for the future of humanity. It could facilitate the establishment of human colonies on exoplanets, ensuring the survival and expansion of our species. It could also lead to the development of new technologies and industries, driving economic growth and innovation. While the practical realization of faster-than-light travel remains a distant goal, its potential impact on human exploration and our understanding of the universe is immense. The pursuit of this dream continues to inspire scientists, engineers, and explorers around the world. Section 9. Summary and encouragement for curiosity. Faster-than-light travel through space-time bubbles and the Alcubierre Drive offers a glimpse into interstellar exploration. Conventional physics sets the speed of light as the limit, But manipulating space-time provides a potential loophole. Rooted in Einstein's general theory of relativity, the warp bubble concept contracts space in front and expands it behind. This relies on exotic matter or negative energy, which are still theoretical. Ongoing research may one day make space-time bubbles a reality. Faster-than-light travel could enable humanity to reach distant stars and explore new worlds. As we explore these possibilities, it is essential to remain curious and open to new ideas.